Notice we have a group up here. So go ahead and raise hands. We'll start here.
Yes, Claes, the General System for Learning, Reasoning and Symbolic Ways. How do you approach compared to genetic programming?
Well, there's no, well, there actually is a kind of recombination when we look for new axioms. But that's a very superficial similarity. So, yeah, it's a quite different approach, I would say.
Is your rule writing system Turing equivalent?
Turing equivalent?
Yeah.
Yeah, I suppose so. Yeah, sure, it is.
Because the experience in genetic programming was that, you know, if you have a way of representing full Turing computation, and you try to sort of elicit programs by some sort of reinforcement process, the search space is just filled with local maxima.
Yeah. So if you look at the functions, we can derive any recursive function, but then we have this addition that we only look at computations that can be made with bound resources. So then we're all of a sudden in the finite realm. That's why we can do it at all. Otherwise, it's out of the question to do combinatorial search like we do.
So one thing I didn't understand is, besides fitting the evidence, your theories, you must have some other selection principle, because there's a different number of theories that fit the data. And I have the same issue about the search mechanism.
Yeah, so our main way of getting rid of most candidates is just to notice that they fail to compute given the resources that we have. So that leaves us with very few, a small set of finite candidates. And then we have selection mechanisms to do the tie breaking. For example, size is the most important one. And then we also have generality, so we prefer general axioms that have variables in them to facts that only contain constants, for example.
So what is the search mechanism in the space of the...
Yeah, the search mechanism is to generate short axiom candidates. And we do that in there's some intelligence involved when we do that. Then we evaluate those candidates using the bounded resources that we have. So if there's a candidate that requires a lot of computational work, we will reject it.
And then, how do you search what?
Yeah, I mean, then once we have selected a candidate, that's what we return. That will be the axiom that we add to our database of repertoire theory.
So how do you get the candidates in the first place?
Yeah, that's we have a few mechanisms, but one of them is to use an abstraction operator, which, for example, takes 2 times 0 equals 0 and 3 times 0 equals 0. From that, it produces x times 0 equals 0 as a candidate.
So that's going to be a very specialized mechanism. In general, what's the principle?
That's one of the principles called abstraction. Another one is this recombinatorial principle, which allows you to generate algebraic axioms and so on. Yeah, there are a number of techniques that we use to generate axioms.
Well, I'm sorry to focus on your paper, but can you give me the context of the strategy for why you want to go to arithmetics that are, when you use the term theory, as you well know, you're appropriating the very same term that's used for the set of all theorems that would be deducible from, say, piano arithmetic, which is generally taken to be standard arithmetic, grade school arithmetic. So I'm not really seeing the connection or the point to general intelligence, because if it's not even basic grade school arithmetic, then it's not the arithmetic that logicians and mathematicians would even be concerned about, right? So can you say something about the context of the work?
Yeah, I mean, the usual approach is that someone, for example, Giuseppe Piano Jürgen will come up with an axiom system, and then the system will use that. So we try to take the approach when the axioms are generated automatically. So that's the thing, and then we can use this in many different contexts. We use the same program for arithmetic and for logic and so on.
Can it learn the axioms, the actual axioms of arithmetic?
Yeah, sure. It learns the piano arithmetic, but we only deal with the delta zero formulas, the simple formulas, and for those the induction axiom isn't needed, but it learns exactly the piano axiom. The piano axioms, for example, when it's exposed to examples from arithmetic.
Thanks.
I don't need the mic, I'm loud. I just wanted to ask all of you who have source code for your projects, is that code publicly available? That's for everybody who has code. Yeah.
Raise your hand if your code is available.
Would you like to tell us more about how to get it? Is it on GitHub? Should we email you? Google it? Google it.
The link is in the paper. Other questions? If the panelists have questions for each other, that's fine as well.
I wanted to maybe real quick, this is to follow up on the rest of the class, but as I understand your work, I mean, one of the main points, at least that I think is an interesting one, is that when you bring to bear the resource constraints, you get very interesting results, and that there's a general fundamental principle here that maybe you're making a point with, right?
Yeah, so that's what the whole thing is about. We try to take into consideration the fact that we want to beat humans at doing certain things, and humans have limited cognitive resources. So we might as well impose similar cognitive resources on our programs. So in that way, we are likely to be able to cut down the computational complexity dramatically while maintaining human-level performance. That's the idea of it. So we're exploiting the human limitations to our advantage.
I have a couple of questions about the error work, actually. I mean, not necessarily specifically about this exact simulation, about error in general. I mean, the two questions may connect to each other. I mean, one is about the scalability of the approach to anything approaching human level intelligence. Given I know it's an extremely efficient software system at the micro level, but still these self-organizing dynamics are very complex, and I'm not clear how you would have any way to predict how scalable it would be in terms of how it would behave at a large scale. The other is what tools exist, both theoretical, conceptual, mathematical, and practical software tools to, I've been talking too much, to understand what's happening inside the network of ERA as it is dynamically evolving over time. Because this is an issue we have in OpenCog as well, even though the dynamics there may be simpler than in ERA. Like, once the attention allocation starts going, it's really hard to tell what the hell is going on inside the system. You can visualize a little bit of it and make a time series of one node's parameters over time. And of course, it's a problem that we'll have in measuring the human brain once we get good enough data to see what every neuron is doing in real time. How the hell will we understand what this movie of brain activity means? So I'm curious for thoughts on either of these things.
Yeah, very good questions. On the scalability, this is of course a hugely important question, and obviously given the ambitions that we have, and the reason for us being at this conference is, I can safely say, we're not there yet. In fact, we don't have very good data yet on the scalability per se. What we can say at this point is that for any task that's similar to the one I just showed you videos of, with lots of mixed kinds of variables, with a high data rate, throughput, closely tied to, or integrated with time, time-dependent learning, the system seems to do extremely well. In fact, much better than we expected. We had actually invested in a 64-core system, and we only used 6 for this. So this is, in fact, good news. But we don't know, how much the rest of the course will improve or do, anything for what kinds of tasks, because we haven't really tried it yet. However, because we know how the system operates under the hood, we can safely say that it parallelizes very, very well, way better than we hoped. So there's some interesting work ahead of us on that. And there's a bunch of questions related to sort of, are some domains worse than others, and tasks worse than others, and so on. And the transfer of learning, how does that work? We're pretty sure that it works much better than any transfer of learning tasks demonstrated to date. But we don't have the data, so don't take my word for it now. Just wait for, well, it'll probably be 2 years before we have the real data for that. So I think I'll leave it at that. And maybe Claes, you want to say something about the tools?
Yeah, so it is, as you say, incredibly hard to see what's going on, especially even as well that the system is highly parallel, so you have to, if you stop it, there's many threads that have to be stopped and inspected, and then you have the memory that contains all the knowledge. It looks a lot like spaghetti, of course, with all the hierarchical links that it's building. So if you want to look at it, it takes a long time to disentangle it. And yes, ideally you would have some tools to visualize it in some more neat ways. And yeah, these are still forthcoming at the moment. So this is something that is indeed bugging us as well.
Actually, we have a much better hope of disentangling this than if this was a giant artificial neural network, because all of our representations are symbolic. So there is a way to build tools to nicely visualize it. But whether we have the time and if we come up with the right ideas, we don't know yet.
I'm not sure how meaningful that distinction really is. I mean, the symbolic system could have an insanely complicated internal dynamic as well. I mean, if you apply the symbolic system to raw persets of a robot, I mean, the logical propositions would involve whether the pixel is one color or another. It would also be very opaque. I mean, part of my question had, what I was thinking is about assignment of credit. There must be something interesting happening inside your system with credit assignment among all these different rules, firing in chains and cycles and so on. But I'm not sure how one would understand what sort of assignment of credit dynamics is happening in there, although it's probably quite interesting.
What was the question?
So look at what you're doing. So this is an interviewing system. So the simplest thing the system could do is just remember all the queries, remember all the answers to the queries. I presume it's doing more generalization or something above that. I mean, at ICT, we build question answering systems all the time. And we just take a list of questions, a list of answers for each, and then we do some simple bag of words generalization on the questions and the answers, or on the questions at least, so we try to give an appropriate answer. I'm assuming that under the hood much more is going on than that. Can you say something about the kinds of generalizations that it's creating, or what it ends up doing that ends up being beyond essentially memorizing the questions and the answers?
Yeah, I should start to say that basically it's not a dialogue system. It's a goal-driven learning system that operates on variables. There's no distinction in this system whether something is a speech act or anything else like that. It's all data, it's streams of data, it's temporal relationships.
But in the seeds that you gave it goals which included
which pointed to
with the dialogue.
Yeah, which pointed to essentially instantiations of objects in the domain of its operation. That could be pointed to anything.
But in this case, it was.
In this case, it was.
Dialogue.
Yeah.
So I mean, that's sort of functionally equivalent to making it, telling it to act as a dialogue system.
That's what it seemed like the laws were
But
doing.
it's,
Yeah.
yes, but it means that there is no, what I'm getting at is there is no components for dialogue in the system, other than the seed, in fact.
Sure. That's worthwhile. I'm still curious about the question Paul asked, which is internally, what kind of generalizations is it building, which is an independent question.
Yeah, maybe I can also go into this dialogue part. It's not just the way it's represented, the sentences that it's going to construct. This is not the only thing that it learns. It has one general learning mechanism which learns all levels. So it's not just constructing sentences out of words, it's also constructing the interview at a higher level. And this uses the same mechanism. So it's domain independent. So this same mechanism can learn to construct sentences and to construct interviews. And
Sure. I mean, it's all sequencing stuff together. Right?
Exactly.
Yeah. That makes sense. It doesn't address the question of how it generalizes stuff, or what generalizations is it learning internally. Maybe you don't know.
Yes, we do know, but
You're not going to tell us.
well, it might take a while to do it properly. Well, it does a lot with basically taking the instances that it's seen already and making models for that unify the instances, and then seeing if those models can actually predict just as well as any of the more specific models of, pertaining to particular instances. So it generalizes by, for example, replacing values with variables, and it does that on time and on concepts, because it can also it combines models hierarchically. So models refer to models, etc., all the way down.
It was not just the dialogues that were learned, it's not just constructing sentences, it's combining it with other modalities as well. So it's asking like, can you tell me more about this? And it's pointing at it at the same time. So it's not just constructing sentences, it comes from all modalities.
Is it correct that the attention mechanism helps to prune which combinations of variables are formed?
Yeah, that's in fact goes to your question about credit assignment. It's very heavily driven by resource management of attention, as we call it, because it's very much. I mean, it's kind of across the whole thing. It's a very general mechanism. It's not as machine dependent as you make it sound when you say resource management. It's really at all levels, and so. It has that extra dimension, which really helps it cut down on the cursive dimensionality.
So could you say, for example, that it learned that when it says this and it points, that, I mean, to some extent, that combination is referring to something. Is there a generalization that corresponds somehow to that, or is it just mimicking that accumulation?
Yeah. There is, yeah. So we're actually improving this on this very point. We've been improving since this demo was made over a year ago, because there are, and in fact, that's one of the reasons why we don't have the tools yet that Ben wants us to make, or actually we do as well, because it's just been so much fun to extend the system, because we know so many ways in which we can improve, including the generalization mechanism. But anyway, to keep a long story short, I think this attention or resource management mechanism is permeating the whole operation of the system, and it's very different from any other system that I've looked at. So I'm not saying that it's the way to do it or the best way to do it or anything of that sort, but I think it's an interesting, different way, sort of along the same lines as classes. Bringing resource constraints into the whole thing does. it removes a lot of problems that I thought, we'd have to solve, but, they just go away. So.
There's one last question from the audience.
I have a question for Éric with the skeptical reasoning. So, I guess I mean, without reading the paper, and the presentation was very, very quick, but it sounds like you're focused very much on using the elements of the reasoning are based on Boolean logic. But on Boolean logic, if I'm correct. Right? So I guess in a lot of cases, you have these two conflicting representations of knowledge, and it's not clear. Say, for instance, if you had two groups of human beings that came up with this, or two individuals, it's not necessarily obvious which one is correct, and you wouldn't necessarily be able to. I guess what I'm curious about, and I'm just curious about your thoughts about it, is that sometimes, or in a lot of cases, what is more likely to be the more reasonable axiom or presentation of things is based on the context of what is being presented, and if you try to decompose the hypothesis, if you like, or the answer, or whatever you're describing, in terms of what you're describing, which is to pull out what you think are to be the most likely things to be true, that would be affected in turn by the context. And it seems to me that that Boolean logic, just by itself, is not necessarily good at, or not effective at dealing with higher order reasoning, which is contextually dependent. I'm just curious about your thoughts about how this works for that type of system.
I think you mentioned several issues, and most of them are very complex to answer in a few seconds. But what I would like to say is that there is only one correct way to deal with Boolean logic. This is one thing. There are also contextual logics. For instance, if you are dealing with non-monadic logic, obviously this is contextual. Okay? This is the first part of the question. So it's possible to move to all the contextual logics, no problem. Despite the fact that the complexity will increase, worst-case complexity will increase. What I agree with you is that there is no one single correct way, the right term, to handle conflicting knowledge. There are many paradigms. And so what I try to show you is that there are several possible ways to handle contradictory information, and all of them are reasonable. And in this way, I agree with you. There are several possible reasonable way to do this bit. And the last point is that we are not stick to Boolean logic, as I mentioned. All we need is a finite satisfiability concept. Because if it is infinite, it's not possible to do this in a finite time. And the only constraint is that we need a capacity theory, saying that any consistent set of information as subsets that are consistent too. And that's all we need to implement this paradigm. What will differ is obviously the time to compute, because if you move to knowledge presentation formalism that is more expressive, more probably you will have a time to compute it that is higher. So I agree, Boolean logic is the basic case, but for instance, we can apply constraint solving problem, CSP, in discrete domain. This is exactly the same thing, the same stuff. You have minimal consistent subset that you can compute them. Okay. But what will vary, obviously, is the time to compute them. This is a whole trade-off in AI. Either you have something very expressive, and in this case complexity is high, or you have small expressivity, and in this case you have better chance to compute. But what I showed is we can handle very large programs because minimal proven inconsistencies that are more than thousands of clauses. This is far more than what human beings can handle. And we can do it very easily for the most difficult result program. So I think that your question addresses several topics, and I can give you 25 points.
Okay, please join me in thanking our panelists.